Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on overview of experimental stress analysis, and what we have primarily focused in the previous class was for typical problems for which you know the solution, we have looked at the kind of patterns you could get from some of the experimental techniques. The problems considered were beam under 4-point bending, cantilever beam, disc under diametral compression, and also clamped circular disc with a central load. In all these cases, you have analytical solution possible for the stress field. So, you have got a closed form expression for the stress field, you have got the strain field and also the displacement field. And what we did was, we did a sample of experimental methods. Some of them were directly from experimental result, some of them were simulated result to give a feel of how the whole field information looks like. So, now your eyes get tuned to how to interpret whole field information to an extent possible. And finally, what we will do is, we will go to the problem of spanner tightening a nut, and as I had told you earlier, due to complex nature of the geometry, only a numerical solution is possible for this problem, and that is what we are going to see. And what I am going to look at is, we have already looked at day to day application of the problem, and surprisingly you do not have solution from strength of materials or even by theory of elasticity. This is primarily because the shape of the spanner is complicated and you cannot define the outer boundary in a convenient fashion for you to do a theory of elasticity solution. And in this case, only a numerical solution is possible. I do not have a closed form expression, so I have to solve this problem numerically. And let us see how the numerical solution is. You have very rich set of results that you get from a numerical solution. And in this case, the numerical method adopted is finite element method, and what you have done is, you have meshed the spanner, and what you find here is, this is the experimental fringe pattern and this is the simulated finite element result of sigma 1 minus sigma 2 contours. And here I want to point out a few things. When I do a numerical analysis, I can get the stress field, I can get the strain field, I can also get the displacements. And if you go to commercial packages, you would be able to plot specific contours. I have a sigma x contour and the software chooses its own colors and then gives you an indication that red means maximum and shade of blue, what you have here, it goes to less value of the stress information. You could see this without mesh, you could also see this with mesh. And for this, you do not have to take the trouble of sketching it, because it is too complicated for you to sketch. The idea is to visualize what way you have the information available from a numerical solution. I have the mesh here and you have a nicely done mesh, these are all quadrilateral elements, and I have the sigma xx stress contour. Similarly, I can also get the sigma yy stress contour, and I can also get von Mises stress contour. And if you look at von Mises, in certain aspects it captures certain geometry features of the photoelastic fringe, but the colors are totally different, because the color is dictated by the standard finite element software package. And what was done was, we have developed a in-house software. What it will do is, it will evaluate sigma 1 minus sigma 2 and also mimic the colors that you get in an experiment, and this is plotted. And a approach like this helps you to quickly come to a understanding that you have very good comparison between what you observe in the experiment and what you observe in the numerical method. And if you look at very closely, I have this as a stress concentration region, and what you have got and what you see in the screen, my students have taken little time to apply the boundary condition appropriately until the experimental fringe pattern matches closely with the numerically simulated results. So, both the choice of elements, discretization, and also the boundary conditions are improved until you get a close match between experiment and numerical solution. So, you have this. What is the difference here? Here, when I have to find out, I can get sigma xx, but I can do this only by interpolation and based on finite element formulation. I cannot go to the location of the coordinates and plug simply x comma y and get these values directly. So, that advantage you had in the case of analytical solution. Analytical solution, the main advantage is, if you have a possibility to solve it analytically, there is nothing equal to that, because the amount of computational effort required is very small. I simply plug in x y, I get the value which I want. The moment I come to numerical techniques, the greatest advantage is the shape of the geometry of the problem on hand does not pose any restriction, but you have to do a lot of computational effort, but you get whole field information. So, I can also get the strain field. Until now you have not seen strain field as a plot, and this is with mesh, and you can also see without mesh. This is epsilon xx. Similarly, I can get epsilon yy. I can also get shear strain epsilon xy here, and I can also go and see the displacement field, and this is what I get here. I have the u displacement, I also have the v displacement. So, what I find here is, when I have a numerical approach, I could get all the 15 quantities comfortably, but the very important aspect is, I must match what I have in the experiment very closely by choosing the boundary conditions correctly. Once I have done this, then I have solved the problem satisfactorily, and a parametric analysis is very convenient when I go for a numerical methodology. And what is seen here is, here I have taken the effort of plotting fringe contours, what you get in an experimental technique, and that requires special software to be developed. It is not readily available in standard packages, and we have this, and this is the best way to compare results of photoelasticity with the actual experimentation. When you do a numerical analysis, you can compare with photoelasticity comfortably. And what I also want to emphasize at this stage is, though we have taken simple problems, we have gone and also studied in the process what are the approximations you do in your analytical modeling. We have taken a beam under 4-point bending, and it bends like this, and it is a 3-dimensional object, it has a cross section, but what you have managed to do in strength of materials, you just take it as a line, that is all you do the analysis. And when I go to theory of elasticity, you do not consider it as a line, but you consider that as a 2-dimensional object. But in reality, because you have fluxing, what you find here is, you also have the Poisson ratio effect becomes very prominent, and what you find here is, this is the compression side and this is the tension side, and this compression side bulges out because of Poisson ratio effect. this may be very difficult to model from an analytical point of view, but experiment looks at all this. So, when I get the fringe pattern is reflective of all the 3-dimensional effect that happens to the model. Some you may have ignored it for the point of view of simplicity. So, that is why I said that experiment is giving you truth, and we also noticed the fringe pattern observed in the beam, there was slight variation on the tension side and compression side if you look at it in a subtle fashion. For a quick look it will appear as if it is symmetric, but for a very closer look it will have small deviation which could be neglected as a second order effects and carry on with it. So, the point emphasized here is the moment you come to experiment, do not discard the raw data. Raw data is very, very important. You may have an explanation to understand what the raw data means. If you do not have the explanation, try to go and find out whether you have made any approximation, whether you can refine any of this, whether, because in engineering what we do is we never want to solve the problem in 3-dimensional with all the complexities. I have also mentioned earlier, the success of engineering is approximation, and if there is possible I would like to work with a 1-dimensional solution. If 1-dimensional solution is not feasible, I go for a 2-dimensional solution. Only we are pushed to the wall that without a 3-dimensional solution you will not get satisfactory result, we go and attempt 3-dimensional solution. The moment you go to analysis of plates and shells, it is actually a 3-dimensional problem. You bring in plates and shell theory approximation and try to live in 2 dimension, you do not want to go in 3 dimensions. So, that is the knowledge that you will have to get. So, what we have done is till now we have done 3 lectures on overview of experimental stress analysis. In the first lecture we essentially looked at what is an analytical method, what is a numerical method, and what is an experimental method. In the second lecture the primary focus was what is the information I get directly from an experimental technique. The idea is you may be able to combine more than one experimental technique and try to get of the 15 quantities some quantities of your interest, but what you get directly is from the physics of the problem, physics of the experimental technique on which it is based. And in the third lecture we try to look at what a whole field information is, because you have to graduate from stress as a tensor at a point of interest, you have to go and find out how the stresses vary over the domain of the model. That was the primary focus. And now what we will do is we will go and find out what is the physical principle each of the techniques is based on. Now, I am not going to get into the details of how to perform an experiment or how to interpret data. My focus is only to bring out what is the basic physical information each of the techniques is based upon, and we will go from the technique like strain gauges to start with, because this is the most widely used technique. And as I have mentioned earlier, in this you get component of strain along the gauge length of the strain gauge is measured, and here you have the typical enlarged view of the strain gauge, and you call this as a gauge length. So, a strain gauge measures only component of strain, it is not measuring strain tensor. And what I have is, to measure strain tensor I need to have 3 strain gauges for you to do it on a free surface, and they have to be pre-aligned, and you also have a name attached to it. If you have 3 strain gauges on a single base to measure the strain tensor, you call it as a rosette, you call that as a rosette. And what you have here is you also have special grid configurations, you do not stop at only measurement of strain, there may be requirements where you may want to directly find out shear stress, or you may want to find out principal stress, or you may want to find out the residual stress component. So, for all these cases you have special grid configurations exist. And in this I am focusing my attention only on electrical resistance strain gauges, and there are many other methods to measure strain. You have mechanical strain gauges, you have capacitance based strain gauges, and we confine our attention to electrical resistance strain gauges, and you have a variety of them available. And what you have to understand is it is a versatile technique and a general purpose stress analysis tool, because if you are working on adverse condition, then also this methodology can be used. You can use strain gauges in below the sea surface where you have underwater pipeline, or whether you have offshore platforms, you can do this. Many techniques may not be able to do it. On the other hand, if you want to find out what happens on the top of the TV tower, I can put a strain gauge and I can have telemetry and then acquire data. So it is a very versatile technique, it is very widely used, and as I also cautioned you earlier, it has to be used with care. And what you see here is you have a array of strain gauges for various applications, and this you have a hole. So this is meant for finding out residual stress component, and I mentioned strip gauges. This is what a strip gauge is. You have a series of strain gauges available in a strip, and likewise you have various grid configurations available. This is from various manufacturers who have given this. And what is the physical principle this technique is based on? And it was reported way back in 1856. It was reported by Lord Kelvin, and he found out a relationship between strain and the resistance of wire conductors. So what he found was, when the resistance changes as a function of the stress applied. It was a very exciting information. So the resistance does not remain constant, it is a function of stress. So it gives you a scope to measure stress or strain from the strain gauge. If it is only that, then the whole instrumentation would have been much simpler. But what do you find? The resistance of a conductor also changes as a function of temperature. So you have a problem. The resistance is a function of the stress applied, is comfortable for strain analysis or stress analysis, but resistance is also a function of temperature, gives you disturbance. And if you look at the technological development, you have to look at how this temperature effect is taken care of. So what you find is addressing the temperature effect is important in the accurate measurement of strain. And if you look at from the physical principle as a technology, it took almost 80 years to translate the physical principle to an effective measurement tool. Why this is so? Because you need to develop technologies where I delineate the effect of temperature and measure only the strain information, whatever the resistance changes because of strain, and it should be easily available for many people to use it, and it took so much time. And recently it also celebrated the 50th year of metal foil strain gauges. And what you have now is the technology is very well developed, and you can measure 1 micro strain reliably now, very precise technique. And mind you, 1 micro strain is 1 into 10 power minus 6, very small quantity. That is another reason why the technology took so much time. Not only the temperature effect, you are measuring very small quantity, you should be sensitive to that. You are measuring 10 power minus 6, and you have to have certain level of confidence in the measurement. That is why the technology took a very long time to settle down, and now we can measure 1 microstrain comfortably. So, what is the physical principle here? Resistance changes as a function of the stress supply. Then we move on to photoelasticity, and though this course we will study in detail photoelasticity, right now we will confine our attention only to the physical principle, and also bring out you have a transmission arrangement, and this we had seen in the beginning of the lecture also, that you have a 2D model of human femur which is analyzed by transmission photoelasticity, and you also have a reflection arrangement, and the reflection arrangement is useful for prototype analysis. And what you have here is, I have a cantilever beam and I have a hole and I put a coating. The coating has the property of stress strain induced by refringence. So, I can get the fringe patterns like this. So, the basic physics behind photoelasticity is temporary or stress or strain induced by refringence. It's the physical principle used is the phenomenon of temporary, because it does not stay. Once the stresses are removed, this birefringence effect is also removed. So, it is a what you are having is, you have to understand birefringence, all that will come when you understand crystal optics. And what we had seen in the last class was, without getting into crystal optics, you have plotted for the problem of a beam under 4-point bending how the contours of sigma 1 minus sigma 2 will look like. You saw them as horizontal lines and it matched with what you had seen in the experiment. So, what you have here is, the physical principle is stress or strain induced by refringence, which is temporary. The moment I remove the loads, these effects vanish. And you have many developments that have taken place in photoelasticity. The photoelasticity is a very versatile technique like strain gauges, and in fact, in 1930s people, when they were developing theory of elasticity, many of those solutions were actually verified by experiments using photoelasticity, and that is what we are going to see. And what you have here is, so you need crystal optics is desirable to appreciate, but we have already said that you can do it by this one. And what you do here is, you use a polarized beam of light for revealing the stress information, and the optics required is fairly simple, and fringes are seen in real time. This is very important. If you go to any one of the experimental technique, for example, if you go to holography, you will have a double exposure. Only after processing you will know how the fringes are. So, you do not have any guidance on, while applying the load, whether the load the symmetry is maintained, all that you will not be able to know. But with developments with computer based processing, you could make even those techniques in real time. So, when you look at any of the whole field optical techniques, one of the aspects you look forward is it providing fringe information in real time, and photoelasticity does that. And data interpretation to physical parameters is easily possible for thin specimens, and the key point here is under normal incidence. So, that you will have to keep in mind. If you are having a curved object, then what you need to do is, you must immerse it in a liquid which has the same refractive index as that, and ensure that you have normal incidence. See, when you go to the finer aspects of any of the technique, there will be restrictions. So, it is a tool, and how good you use the tool, you get the information. So, whatever the experimental technique you look at, you have to look at its positive aspects as well as its limitation. Within that constraint, you should employ those experimental techniques. And I have mentioned that data interpretation is easy for thin specimen or normal incidence. You will appreciate only when you go to other techniques how difficult the data interpretation is. In this case, it is so simple that we will establish it based on crystal optics at a later point in the course. We have already seen from solid mechanics point of view that you get sigma 1 minus sigma 2 contours. And this technique has advanced mainly because you have a unique technique called stress freezing, very interesting aspect, and that has made the application of this technique to 3-dimensional industrial problems. Analyzing the problem as a whole is very difficult, and what you do here is you take the advantage of analyzing the problem as a whole. At the same time, from analysis point of view, you still live in 2 dimensions by slicing the model into thin slices. So, what you have here is many industrial problems, whatever the engines that you see across, whatever the nuclear reactors you come across, they have all gone through mandatory 3-dimensional photoelastic analysis. That is why the designs have become perfect, and designers particularly, once the design has stabilized, they would be very hesitant to change anything, because for any changes they would have effected, there would be a history. Once it is optimized and stabilized, they do not want to change it, and in those stages you need very good tools for you to give the pertinent information. If somebody copies your design, that is a different matter, he does not require any test. A person who develops a design from fundamentals, he needs to go through experimental methods, he needs to worry about analytical understanding, he needs to use even numerical technique appropriately and arrive at a final design. And if you look at in early stages, 3-dimensional photoelasticity has played a very significant role, and particularly because of a very interesting phenomena called stress freezing. We will see that detail later. Now, you are being sensitized on what are the possibilities. So, this is what in the case of transmission photoelasticity. On the reflection photoelasticity side, people have also developed a spraying technique to put the birefringent coating on large industrial components. One of the component that people do is aircraft landing gear, which is very huge, and they still do structural optimization based on photoelastic analysis, and this model will typically cover a 2 to 3 story building height. It is not a small model, you are actually working on suppose they want to develop A380, they would have only rig for the previous version A320 or A330 or A370, and they would use that loading jig to make a 3-dimensional photoelastic model, put a coating and do some structural optimization, then finally develop the landing gear and put it in a loading rig and finally verify. So, it is done for huge problems on one spectrum. On the other spectrum, in dental mechanics, if you find they put a floss, they put a wire which goes round your tooth to hold it in place, those clamps are also analyzed by photoelasticity. So, it is a very small model. On the other hand, you have a very huge aircraft landing gear. So, the range is very vast, and it depends on the user how he uses the technique. And like strain gauges, it is versatile, general purpose stress analysis tool. And when you go to each of the technique, what you will find is there are many branches. This is only a first level course on experimental stress analysis. I would essentially focus on strain gauges and photoelasticity because they are the most versatile, but we will have occasions to look at the physical principle behind other techniques, because each technique by itself is very vast. If you take photoelasticity, we have looked at only 2 variations, one is transmission photoelasticity, another is reflection photoelasticity. If you go to photoelastic literature, you have dynamic photoelasticity, you have photoplasticity, you have scattered light photoelasticity, you have integrated photoelasticity, there are many branches, and now you have digital photoelasticity. So, you have many branches. To cover all of them in a single course is beyond any human effort, So, you need to do multiple courses, and what you have here is photoelasticity is always an ideal tool for teaching the field nature of stresses to beginners. And here I must tell you, stress concentration you all know right now. I have a plate with a circular hole, I have a plate with an elliptical hole, and I have a plate with a crack. Now, anybody in engineering will know what stress concentration is, but if you look at the history, people had, mathematicians and stress analysis had acrimonious debate. Mathematicians used to say an infinite plate with a small hole is equivalent to a plate without a hole, and only with experimental judgment and other aspects they were able to convince whole lot of things happen the moment I introduce a stress concentration. So, people understood there is something stress concentration which you cannot neglect it, and really when you look at what you find here is I have a uniform stress field if I do not have a hole. The moment I have a hole, the stress field becomes biaxial. It is the stress field is also, the stress magnitudes are very high in this zone and also in this zone. This is one thing stress concentration means, stress magnitudes increase, that is one thing. Just not that, even the stress field essentially changes. And it was Inglis in 1913 who said that when he analyzed an elliptical hole, he could do that by theory of elasticity. His result showed crack is not innocent and crack is potentially dangerous. That is the time that fracture mechanics has not developed, and a new branch of engineering, fracture mechanics, came into existence once people understood that cracks are more dangerous. And what you see here is, I have a crack, and crack where you have the least amount of material is removed, and suppose I take the load as 6 in all the cases. I have a plate with a circular hole, I have a plate with an elliptical hole, I have a crack, and you do not need to explain. You see very few fringes here, you see slightly more number of fringes here, and you see I have not put that as 6, I put that as 7, when I put it at 6 you have a large number of fringes here. So, if you have an appreciation of looking at fringe information, the density indirectly indicates the stress levels are high. So, for a beginner you get the field nature, you understand what is stress concentration, and you may wonder, I have an elliptical plate, all these cases are finite geometry, I have a finite width and I have a circular hole. Analytically what I could do is, I could do an infinite plate with a very small circular hole, and here I will have a polar coordinates to determine the boundary condition on the inner surface, and when I go to elliptical hole, you have elliptic coordinates to specify the boundary condition on the inner surface. At infinity you could consider it as a large ellipse, you could consider it as a large circle, that is the way you can approach the solution. So, for infinite plate with small circular hole, infinite plate with small elliptical hole, you have analytical solution possible, and this goes by the person who has first solved the problem. You have this as a Kirsch's problem in theory of elasticity, this as Inglis problem, and once you come here many have contributed. Westergaard solution is very prominent, Williams solution is very prominent. So, in theory of elasticity, when they analyze infinite geometry with any one of these defects or cutouts, you have a name attached to those problems. So, photoelasticity is very good to understand stress concentration, to understand the field nature. Without much effort you are able to get it, and you get a closer picture when I have a look at it like this. Some of you have already made the sketch, and I would like you to make a sketch of it, and the essential features. You have this kind of a fringe field, and you have a fringe field like this, you have fringes forward tilted and so on and so forth. So, now what we will do is we will move on to the next experimental technique. We have already seen that Moiré is what we have used for finding out the displacement information, and we will see what Moiré is all about. And what I am interested to show here is Moiré has an effect of magnifying the displacements. That is the way I am going to look at it. And what you have here is, in the case of metal forming processes, what they have is they have a billet and they will put a grid. You can see the grid here, these are known as grid methods. And what I have is, when I do the metal forming operation, I do a large plastic deformation. So, I am really talking of a very high value of strain, and in this you do not require fine measurements, even these grids deform like this. So, you get very valuable information on the nature of strain field from this. So, you have very large plastic deformation, and for all those metal processing application, people use the grid method, because that itself is sufficient to give you some information. And you could see here I have the grid initially and I have the final grid so much deformed. So, I can really make some kind of quantitative information from this, and in fact the credit for this goes to Professor P. Venugopal of the manufacturing the materials and metallurgical engineering department, IIT Madras. And what you have seen is a Gudgeon pin, that is what this information shows. And so, people have always looked at, they have put a grid, they have always wanted how to go and find out very small deformation. This is for large deformation, it is okay. Now, what people did is, people also, to simplify strain measurement, what you can do is you can have a not only the grid, in the grid you also put a circle. I will show a magnified view and then you see the animation for 2-3 times, you will have an appreciation. I have a circle, I have a circles marked and they become ellipses, circles marked become ellipses. Can you see that? So, what you find is, you also find the stretch direction, and by looking at the change in the geometry of the circle, you will also be able to find out some information about the major strain axis, minor strain axis, and so on and so forth. So, you are able to, from the grid, if you also put a circle, its advantages. So, I have a circle that gets deformed to an ellipse. And now, what I am going to do is, people felt that instead of just using one grid, if I have more than one grid, it makes it little more comfortable. That is how Moiré started developing. And what you find here is, I have a specimen, on the specimen I have a grid and I view it through another grid like this. And what you find here is, I have only stretched it slightly, but I see a play of fringes on the specimen. I am able to see the fringes, they are horizontal fringes. So, what we have found is, people have used initially grids, then they improvised it and put within the grid a circle, you get little more information from the deformed picture of the grid. Then they realized that if I put not one grid, but I put one grid on the specimen and view it by another grid, I get little more information. And somebody asked me what is a grating in one of the classes, where we said what Moiré gives you directly. And what you have here is, this is the grating, this is the grating here, and this is nothing but horizontal bars here. And when I put another grating which is very similar, you see beautiful fringes, when I rotate them relatively. So, what you have here is, it is by mechanical interference you see these fringes. Moiré is not a optical interferometry technique, it is a mechanical interference of the grids that is what you get it. So, I get this when I rotate it relative to the other, I also get it when I translate it with respect to the other. Okay. So, the idea here is I get these nice patterns and I can interpret it appropriately if I conduct the experiment very carefully. Okay. Here I have shown very coarse grids. Suppose I have fine grids, I have you are not able to see the grid lines at all, and the fringes are lot more smoother. If I have these grids finer and finer. Okay. And here I am not making any stress analysis, I am only showing you mechanical interference of true grid patterns, and the grid patterns can be anything. And I have this, and I have a radial lines, and when I put the radial lines, so beautiful. Maybe in Tata Salt I think they have this as the pattern for on that cover. So, in if you do saree design or anything, if you want to have interesting patterns, you could get from some of this information and do it. I am just translating and rotating the grids with respect to each other, I get nice play of patterns. And what you will have to look at is, you have to develop this into an experimental technique for you to extract information. And like friction, Moiré is a nuisance. Friction is a nuisance in some application, friction is needed in braking. You need friction, without friction you can't have brakes. So, you do not want friction in certain applications where the IC engines you have this piston ring moves, you want this to be as smooth as possible. And now you have another set of grid pattern where I have concentric circle, and I relay and when I move both the grids, I get different set of patterns. So, what you have here is, this is called a grating, and one is pasted onto the specimen and view it with the another one. So, you have a master grating and specimen grating. So, what we come here is, if you look at this diagram very carefully, compared to that, this is a simulation where I have some control on what way I move the specimen grating, and here the specimen grating is a checked pattern. I have reason for it, because I have also mentioned in some applications I get only one information, in some application I will do one experiment, I will try to get two information, we will see that. And what you find here is, this moves slightly, but I see a number of fringes. So, indirectly you can understand that it is some sort of a magnification effect that Moiré helps you to measure. So, I want to measure very small deformations, and Moiré helps better than the grid. And if I want to go for finer and finer information, I need to have finer and finer grids. So, Moiré fringes are spaced broadly, indicating a magnifying effect to measure small deformations that cause the formation of these fringes. And if I want to improve the accuracy, I need to have finer and finer gratings, that is what I want to do. So, if I have a finer grating, I have a better chance of measuring small deformation. And what you have here is, I have two grids, I have this, I call it as master grating, this attached to the specimen which is pulled, because of Poisson ratio effect the thickness comes down, and you see horizontal fringes as well as vertical fringes. So, that means what? You have to interpret horizontal fringes separately, because we have always seen I have a grating, whatever the fringes perpendicular to the grating direction, you will find out whether if the grating is aligned in x direction and you get the v displacement, if the grating is aligned in the y direction you get the u displacement. Here I have a cross grating, so I get simultaneously u and v displacement. And strain is a tensor, once I get displacement information I can also find out the slope, that is nothing but the strain. And if I want to strain tensor, I need three information. People also have developed a grid at 45 degrees superimposed over that, And I also caution, experimentalists, when they develop the technique, they develop it and see what maximum information you can get out of it. But from a user point of view and data interpretation point of view, it is always better that you have one information at a time, okay, because you get much better information when you want to do that. So, the fineness of the grid spacing determines accuracy obtainable in Moiré, and that is what is shown here. And let us look at some numbers. Okay. So, what you find is, if you look at the Moiré literature, the grid line spacing, how fine it is, was a very big challenge for scientists to develop. And when you think of Moiré, you cannot forget the contributions by Daniel Post and his co-workers. They have developed the technique very well, and as the grating density is increased, I will also have to bring in diffraction effects for interpretation. So, what we find is, grid you can easily analyze, and I can have some grating, I can use just the geometric information and then interpret the fringes. That is what you call the geometric Moiré. Suppose geometric Moiré, we find the limitation, for me to make finer measurement, I need to go in for finer number of lines. Then you find, from optics point of view, diffraction effects have to be brought in and do for interpretation. So, the interpretation becomes little involved as you go by. Fortunately, whatever the equation that you develop in geometric Moiré is also equally applicable for Moiré interferometry. And what we do is, we decide this based on the lines per millimeter. If you have 40 lines per millimeter, up to that you can interpret it based on geometric Moiré principle, and the displacement resolution is of the order of 25 micrometer, and 40 lines per millimeter is very fine. That itself is very fine. It is not you imagine you have millimeter is so small, and within that you have 40 lines, black and white lines. So, it is not something very high, it is very fine, and you will have to be worried about that. And what you can do is, from Moiré data, strain has to be obtained by numerical differentiation. So, it is better that you go for Moiré interferometry, where you have finer displacement measurement. Now, let me ask, suppose I want to measure 1% of strain. Does 1% look small or big? You go to a bank and ask for a loan, if he says 1%, you will definitely go and take the loan, because you find 1% is small. But some of the smart banks, what they do is, they may say 1%, but 1% per month, that means 12% per year. Okay. On the other hand, if somebody gives you 1% as your interest for your investment, you will never put the money. 1% in strain analysis, is it small or big? Some say small, okay. It is not so, it is a very huge value. And what I want to caution here is, I said that long time back, I said the example of somebody going to a doctor and then finding out whether 105 degree temperature is small or big. He should not refer an encyclopedia. And when you have difficulties in finding out the yield point, which is not marked sharply, then what you do is, you have the offset method, and then you locate the yield point on the curve, stress strain curve. I have an alloy steel which is pulled here, and I have the stress strain data, and this is what I have. I do not see very clearly the demarcation of going from elastic to plastic. It is very smooth. What is usually done is, you draw an offset at 0.2%, and 0.2% corresponds to 2000 microstrain. And what you have here is, I have this as the proportional limit, and this as the elastic limit, and you have the yield strength. So, what you find is, at 2000 microstrain, the material has yielded, but you permit that for you to find out what is the yield strength. of the material when you are not able to accurately locate it in your stress strain curve. And many actual components, they work under the, I have components interacting with one another, and I can't have large strain. I have to live much below 2000 micro strain. So, typically you will live within 1000 micro strain or so, you will not cross that strain in many of your mechanical and aerospace components, where you have mating members and you can't have large deformation there. So, 1% of strain looks small, but it is not small from strain analysis point of view, because at 0.2% of strain the material has yielded. So, many of these techniques, you work only regions beyond yield. So, if I have to come and measure lower strain, then I have to improve my experimental refinement, data acquisition, and how do I do the experiment, so on and so forth. And that is what is done, in the case of Moiré. So, what you find here is strain sensitivity can be improved with high density gratings, and what you find is 2400 lines per millimeter is now possible. It is the theoretical limit, people have achieved the theoretical limit by real hard work, and with such high density grating I can measure 0.417 micrometer. But look at other thing, if I have one fringe is 1 millimeter, Moiré fringe spacing is 1 millimeter, the strain accuracy is only 417 micro strain. And I said we want to work much below 1000 micro strain. Okay. So, Moiré interferometry has a limitation, it cannot go below a certain level. So, it is good for large deformation problems, it may not be good for small strain measurement, but certain specific applications the method of Moiré is very good. So, that is where domain of application you have to find out. So, what you find here is the grating pitch of this high order has been used, and like I said, you have various photoelastic methods. I have geometric Moiré, that is what you had seen in some of those simple examples. Then you have several variations, you have shadow Moiré, you have reflection Moiré, you have projection Moiré, which cater to different field problems. And if you recall, we had seen reflection Moiré has been used for finding out the curvature in the last class, and geometric Moiré is useful to find in plane as well as out of plane displacement, and also slope in bending of plates. So, you have to use a particular kind of Moiré for a particular application, like you use reflection photoelasticity for the prototype analysis. You will also use, if I want to find out outer plane displacement, I will go for geometric Moiré, I will go for shadow Moiré, and then if I want to find out curvature or slope, I will have to use appropriate Moiré method, and if I want to have finer and finer measurement, I will go for the Moiré interferometry, I can go for very small measurement of strain. And do you have any questions at this stage? Yeah.
You have said it is used for large deformation,
yes,
significant, so it cannot be used for any elastic.
We will see that later. I mean, if you look at IC chips, a lot of thermal stresses are developed. If you go and look at any one of this electronic packaging, people have now developed semiconductor technology to the extent you can pack as many transistors in a very small place. But one of the challenging problem there is the heat generation, how the heat generation is dissipated, and people have done very interesting experimental approach using method of Moiré to find out the stresses on the IC chips, the legs, and all those electronic packaging components. If you want to look at that, Moiré is the only technique which can reveal that. So, you have to select a technique for a given application. Now, you have digital image correlation, you have grid method, these are all for large deformation problems, but for small deformation you have to use, if you are able to use a strain gauge, well and good, I can go up to 1 micro strain, but I can't put a strain gauge on electronic packaging because that is comparable in size, so you will not do that. And if I want still finer measurement, I can go to holography and find out very small displacement. For nano mechanics, people use holography very well. So there is nothing like one technique has to be patronized, other technique has to be dropped. For the problem on hand, which technique is ideal, that is one issue. Another issue is whether you have the facilities to do that. You may have a technique available in the literature, but you should also have facility, because experimental facilities are expensive, and you may want a design answer yesterday. Okay, that is how industries come, they want result yesterday, when they come today they want result yesterday. So you have to solve the problem in a very shortest possible time. So we will also discuss towards the end of this overview of experimental stress analysis a detailed discussion on how do you go about selecting different techniques, very general guidelines. You may not have, there is nothing like one-to-one matching for you to find out the technique for a particular problem, you can have multiple techniques. So it depends on various factors. Thank you.